So let's check out practice 12.1. And I'm calling this 12.1, but these are questions that are all through chapter 12, actually. So let's just look at the first question here. And we want to take the derivative. And so what we're going to do is we're going to take the derivative of both sides. And the derivative distributes So I distributed the derivative to each term. Now, this isn't necessarily a step most people write. In other words, what most people do is they go from here and they realize, oh, I can take the derivative of each term, and then usually their next line of work then is that derivative. I want to show that we have a constant here, so we can pull this outside the derivative. We have another constant here. We can pull that outside the derivative. So if we look at the first term, x cubed, so the 3 drops down, subtract 1 from the exponent. Then we have our minus sign. The 16 pulls out of the derivative. And then we multiply by what is the derivative. Derivative of x squared is 2x. And the 45 pulls out of the derivative. And then the derivative of x is 1. And then the derivative of a constant is 0. And so we're left with cleaning it all up. Check out the next one. So they're going to give us a different letter this time instead of x. Mix it up a little bit. So we can take the derivative term by term. So let's do this first term. So we have the constant times the derivative. So 0.8 drops down. And then we subtract 1 from the exponent. So 0.8 minus 1. And then we go to the next term. We'll do this derivative. So we'll have minus 5, our constant. And then we have 2.7, which will drop down, be our coefficient. And then we subtract 1 from that exponent. So 2.7 minus 1. And we'll clean this up a little bit. We got 6.4u. And check out the next one. So we're going to take the derivative of both sides. Remember, the derivative distributes, so we can do each of these term by term. So we'll do this one first. So the constant, and then the derivative of x squared is 2x. Then minus 6x. The 6 is the constant. That pulls out. And then the derivative of x is 1. Then we'll have minus 8, this constant. Taking the derivative then of x to the minus 2 becomes the coefficient. Subtract 1 from the exponent. And then we'll clean this all up. So number 4. Now notice the x is here in the denominator. But that's not a problem. So using the properties of exponents, remember we can take an exponent and bring it across the division bar, and that changes the sign of the exponent. So we'll take the x to the 6, bring it across the division bar. That changes the sign of the exponent. Bring this x across the division bar. And so we have power function, power function, power function, constant. So when we take this derivative, we're going to do a power function here. So minus 7 drops down. So minus 7 times 4. Subtract 1 from the exponent. Go to the next term. The minus 6 will drop down. So minus 6 times minus 7. Subtract 1 from the exponent. Minus 1 will drop down. Minus 1 times 5. Subtract 1 from the exponent. And the derivative of a constant is 0. Number 5. So here's another one that takes a little prep work. And this is something that can happen where you have to kind of prep the function to get it into the patterns, to the forms that we're using. Because so far, we haven't talked about how to deal with division or multiplication. All we've talked about so far is when functions are added or subtracted. So like in the numerator, if functions are added or subtracted, that's no big deal because the derivative distributes, which means we can do them term by term. However, we haven't talked about what happens when you have functions that are divided. And we will. But what they're looking for here is to decompose this back into fractions. So it's kind of like working fractions backwards. You know, when algebra, you may have something like this. You find a common denominator, then you bring them together. Well, here, we're going to break them apart, put them back into their fractions. And why is that useful? Well, x to the 5th divided by x gets us 2x to the 4th. And this x we can bring across the division bar and make that exponent negative. And now we have two power functions. All right, gonna do that one again because I copied the function wrong. I had x in the denominator when it's actually x cubed. And do the same thing again. Decompose it into fractions. And now we have 2x squared plus 5x to the minus 3. Bringing this across the division bar changes the sign of the exponent. So now when we take this derivative, 2 drops down, 2 times 2 is 4. Subtract 1 from the exponent, so we get 1. You don't commonly write exponent of 1. Minus 3 drops down, hits the 5. Subtract 1 from the exponent. And there we go. Number 6. So we got our function. They want us to find the slope and the equation of the tangent line at the point x equals 2. So we'll need the derivative. So do them term by term. So the derivative of x to the 4th, 4 drops down, subtract 1 from the exponent. For x squared, the 2 will drop down, hit to minus 25, they get minus 50, subtract 1 from the exponent, and the derivative of a constant is 0. So here's the derivative. The derivative gives us the slope of the tangent line, and they want this specifically at 2. And there's our slope, which is the first part they want, just the slope. And so to get the equation of the tangent line, we need the y-intercept still. So we have the slope part, but now we need to get the intercept, which means an ordered pair. So we have 2. We need to figure out what y equals at 2. So we'll have to plug that into the function. And so we get our ordered pair is 2, 60. This is the point the tangent line must go through on the function. And so now we have our slope, which was minus 68. And we're going to plug in then our ordered pair. So when x is 2, y is 60, And we will get 196. And then that is B. So question 7. So we've got 3e to the x plus x to the 7th. We want that derivative. So because addition or subtraction, if functions are being added or subtracted, we can do the term by term because the derivative distributes. Remember, this is going to be different for multiplication and division, though, which is coming up. So for addition and subtraction, the derivative distributes, and we can just do these derivatives term by term. So the derivative of e is itself, and then we have a power function and the power function derivative. So number 8, so derivative distributes. We can do these term by term. So the derivative of an exponential is log of the base times itself. And my arrow is going to have to curve over like that. So 3x to the 4th, a power function. So we have an exponential pattern. Now a power pattern. So the 4 will drop down. 4 times 3 is 12. Subtract 1 from the exponent. And the derivative of natural log is 1 over x. And the last one so we have an exponential pattern, a power function, and a log. So we have to identify the functions we have so we know which derivative pattern to use. So we're going to have 5 times the derivative of an exponential, which is log of the base times the exponential. Going on to the next, the power function. 9 drops down, hits the 2. Subtract 1 from the exponent. And then to the last function, which is a log pattern. And the derivative of natural log is 1 over x times the coefficient there. And there is practice 12.1.